This over.
There's another.
Okay.
Yeah. All right. Well, don't worry, we'll have plenty of time for lunch. Okay, so. Are happy to have John Etnyre to continue the morning's program. So John will talk about symplectic rational homology ball fillings.
Well, thank you very much. And I'd like to really thank the organizers for the opportunity to be here to speak and to getting the technology sorted out. And let's see, I'll try to talk a little bit fast and maybe we're not going to be too late for lunch.
No, please don't.
Okay. Okay, and now it's not allowing, okay, there we go. So again, I should just, before I start, this is all joint work of Barak Pachi and Bülent Tosin. Anything I say that's original in this talk will be joint work with them. Great. So a fundamental question in smooth topology is trying to understand when a rational homology sphere bounds a rational homology ball. And just reminding you here that I just mean for a rational homology sphere is that the homology of the manifold Y is the same as the homology of the sphere, and of course the same for a rational homology ball. Another way to say this is you're asking what are the zero elements in the homology cobordism group. So there's been a lot of constructions of these things. There's probably some before this, but one of the first papers that I know of that really takes this question seriously is a paper of Casson and Herrer from 1981. And they use a lot of really fun construction, surgery theory, handle body theory, branch covers to build such fillings. And there's been tons of papers since. I actually started to try to write everything down, and it just would have taken the rest of the talk to tell you about all the papers. But more recently, in the last 4 or 5 years, there's been a ton of people working on this. Here's a handful of them. So along with constructions, you like to obstruct things. So which homology spheres don't bound rational homology balls? And the first such obstruction came from the Rokhlin invariant, which basically says if it's non-zero, it can't bound even an integer homology ball. So for instance, the Poincare homology sphere can't bound an integer homology ball. This can be improved. Finchel and Stern define this kind of R invariant. And from that, they actually proved that any connected sum of copies of the Poincare homology sphere can't bound a rational homology ball or integer homology ball. So I'm going to go between integer and rational. I'm going to mainly stick with rational, but when I can state it for integer, I will. Froeschov also defined another invariant called the H invariant. And there's been a ton of recent invariants using Hagar-Plur theory, Seifert-Witten theory, and most recently, Manolescu defined some invariants. It was able to prove that if the Rokhlin invariant is non-zero, then no connected sum of that manifold could possibly bound a rational or an integer homology ball. And kind of the amazing thing is, this is a very natural question, but it also has an amazing implication that there are manifolds in dimension 5 and above that don't admit triangulations. So basically, Galowiecki, Stern, and Matsumoto proved that if you had such a sphere, then you would have these non-triangulations. Then Manolescu actually proved that that any sphere with Rokhlin invariant 1 can't, well, is infinite order in the homology cobordism group. So this question has a lot of interesting implications in the smooth world, but of course today I want to talk about the symplectic world. And why might you be interested in the symplectic world? I'll remind you, there's this construction from the 90s, a construction of Finchel and Stern, that says if you found a configuration of spheres that looks like this, you can remove it and replace it with that. And they built tons of exotic manifolds this way. And then a little bit after that, Margaret Symington showed that this construction can be done symplectically. So knowing that this collection of spheres and this rational homology ball have symplectic structures with the same contact structure on the boundary, you can actually then do some cutting and pasting in the symplectic category and prove these exotic things are actually symplectic. There's a lot of questions you can ask about when a contact structure bounds has a symplectic filling that's a rational homology ball. Like one of the questions, there's the Gompf conjecture that basically claims that no Briesborn sphere should symplectically bound a rational homology ball with either orientation. There's not been a lot of progress on this, but I'll mention a little bit of that, a little progress a little bit later. Another natural question is if you look at spherical manifolds, these are manifolds that are quotients of S3 by some group action that preserves the Riemannian structure. There's a lot of these, and you could ask which ones have been bound. These are natural rational homology spheres, so you can ask when do they bound rational homology balls. So Liska completely answered this question. I can't remember, it's maybe the early 2000s, I think. And he basically said a lens space bounds a rational homology ball if and only if the parameter P is a square and Q is, well, this quantity m times H minus 1. To tell the truth, what he did is he proved for one particular contact structure, this is true. And then some work of Christian and Lee, and independently myself and Roy were able to prove that all the other contact structures just don't bound them at all. So then you get this complete result about when a lens space can possibly bound a rational homology ball. So that's just kind of a sample older result. Okay.
Also, John?
Yeah.
So for the B-scoring conjecture, is with any contact structure and then whether.
So, I mean, you can interpret however you would like. I think he meant it. Well, since he says either orientation, I think you must mean any contact structure, because with when you reverse the orientation, you don't have the natural kind of one coming from algebraic geometry. So yeah, certainly that's the way I've interpreted it. I think that's what he meant. So today we're going to focus on small Seifert fibered spaces. And let me just remind you, a small Seifert fibered space is, you can think of it as just an S1 orbifold bundle over S1 with 3 singular fibers. And I prefer to think of it from this surgery picture, which I had on the first page. So any small Seifert fibered space you can describe from this surgery picture, where the E naught is an integer. It's going to be very important for us. And the RIs are all between 0 and 1, but the coefficients on these other ones are -1 over the RIs. So this is kind of a normalized form, and every small Seifert fibered space is uniquely described in this way. And we'll see that this E naught plays a really important role when you're trying to study these things. Since we're interested in rational homology spheres, you might ask, when is one of these things a rational homology sphere? And it turns out that they are a rational homology sphere if and only if this invariant E is not equal to 0, where E is just E naught plus these RIs. So in some sense, almost all of these small Seifert fibered spaces are rational homology spheres. So here's a huge family of things that we can try to study. Okay. So here's the first result. So remember, we have this invariant E naught. It's just the coefficient on here. It could be any integer. And we can prove that if E naught is less than or equal to -5, then no contact structure on these things bounds any symplectic rational homology ball. But I should remind you that actually, smoothly, a ton of these things bound rational homology balls. In fact, I'll give you specific constructions of rational homology balls that whose boundary is smoothly some of these Seifert fibered spaces. But none of them carry a contact structure that can be symplectically filled by a rational homology ball. So that's E naught less than or equal to -5. It turns out when E naught equals -4, -3, or -2, there are some links of normal surface singularities that do bound rational homology balls. And here's an example. So this is some kind of plumbing picture. This plumbing picture corresponds to that small Seifert fibered space. So this is an example where the E naught's -2, and it turns out there's seven families. That's just one of them that bound rational homology balls. When E naught's -3, there's 2 families, and when E naught's -4, there's 1 family. I didn't want to draw them all out, but that's just kind of what they look like. Great. So so when I'm going to just abbreviate the sigma E naught R1, R2, R3 divide Y. And if E naught is less than or equal to -3, or if E naught's -2 and Y is in an L space. So by L space here, I mean a Hegardt floor L space, which just basically means the Hegardt floor homology is as simple as it possibly can be. Then Y admits a unique contact structure that bounds a normal surface singularity. So for everything with E naught less than or equal to 3, or -2 with an L being an L space, you have this C canonical. And this thing is frequently called the Milnor fillable contact structure. And there's a series of papers all involving subsets of this group. I don't remember exactly which combinations you take, but Stipschitz is always part of that subset. So they basically prove those 10 families I mentioned earlier all bound, the canonical contact structure always bounds these rational homology balls. And I'm going to note the set of these 10 families by script QHB. So you might wonder, Are there is there anything else that bounds rational homology balls? Sorry, I should say, the latest work, 2011, Symplectic and Bhupal, proved that basically, if you're sticking to this canonical contact structure, the only fillings are the ones that came from these 10 families. But what about other contact structures besides the canonical contact structure? And that's the point of our next theorem that says when E naught equals -3 or -4, then you bound rational homology ball if and only if you come from that family and the contact structure is the canonical. And I should point out, these particular small Seifert fiber spaces, frequently, they can have arbitrarily many tight contact structures, in fact, fillable contact structures, but there's only one that can bound a rational homology ball. Okay, so notice I just did the -2, -3, -3, -4. Notice, of course, -2 is a little bit more complicated because you have these extra conditions. So let's try to see what happens for the -2 case. But before I do that, I need to give you a little bit of notation. So we know in the cases we're discussing, so E naught less or equal to -3 or or E naught equals -2 and Y of L space, that every tight contact structure comes from some Legendrian realization of that link and then Legendrian surgery on it. Okay. We're going to call each of those kind of strings of the AIJs a leg of the diagram. So an example here is this Legendrian link. If you do Legendrian surgery, you get a contact structure on sigma-3, whatever. Okay. So we're going to call a contact structure consistent if so when you realize this thing, you have to stabilize sometimes to get the right framing so that you actually get the right contact structure. If all the stabilizations are done in the same direction, we call the contact structure consistent. If they're all the same on each leg, then we call it almost consistent. So here's a consistent thing, all the stabilizations the same. Here, these stabilizations differ from those, but on any one leg, the stabilizations are the same. So that's almost consistent. So now we can state the theorems for the -2 case. So if Y happens to be in the script QHB, this family found by Bhupal and Lipschitz, well, and the rest of them, but they had the final result on that, then the only contact structure that can be filled is the canonical one. So again, those things can emit arbitrarily many different tight structures, but there's a unique one that can be symplectically filled by a rational homology ball. And if you're not in that family that was already studied, and you're in L space, then any contact structure that can be filled must be either consistent or almost consistent. And of course, there's a very quick little corollary of this, that sigma -2, whatever, if it's an L space, then it can have at most 4 contact structures that are symplectically filled. So it can't prove there's a unique one, but there's at most 4. And that's just because if you look at the way that you can consistently stabilize things, that's pretty much all you get. Well, maybe you get 8, but if you just kind of flip the stabilization to the other side, you actually have the same contact planes, just with the opposite orientation. So I'm not counting those as different. So great. So we can't prove 1, but we can prove at most 4. So I want to move on to E naught bigger than or equal to 0. So we've handled everything less than or equal to 2. Well, a lot less than or equal to 2. There's still some -2 that we don't know about. So what about E naught bigger than or equal to 0? It turns out that those are a little bit more complicated. And what you do is you look at this surgery diagram. So here I've got a 1 handle attached to the 4 ball, and then I'm going to do these surgeries. And these SI can be determined by the RI by some Ralston twists. I don't want to go into the details. If you want to know more, I'm happy to say more, but let's just leave it at that. These SIs determined by RIs. And contact surgeries on these things will give you all possible contact structures. And we have a similar theorem that when E naught is bigger than or equal to 0, then there's at most 4 contact structures that could possibly have rational homology ball fillings. And there's one particular contact structure we can guarantee that if there is a filling, it's unique. There's a unique such filling. And it turns out it's the same as the E naught case, that basically the 4 comes from consistent or almost consistent once you kind of turn these things into a plumbed chain of integer surgery so that you actually get a 4 manifold. Okay, great. So this brings us to -1, right? So I told you something about every E naught except -1. And when -1, in the -1 case, we have this condition that guarantees that no symplectic, no contact structure is filled by a rational homology ball. But interestingly enough, we can prove that in the E naught equals -1 case, there, you give me any n, I can find a contact structure, a Seifert fiber space that admits at least n different contact structures that admit rational homology ball fillings. Remember, in every other case, I could say there's at most 4 and usually just 1. But when E naught equals -1, we can actually get an arbitrarily large number. Yeah. So, I mean, just to make the comment, if you've ever looked into the contact geometry of small Seifert fibered spaces, everything is very easy to understand and uniform as long as E naught's not equal to -1 or -2. And -1 is where everything crazy happens. This is where you get, tight not fillable, things that don't have tight structures at all, just all sorts of crazy stuff happens at E naught equals -1 for some crazy reason. And we're seeing it here as well. This is by far an outlier in what happens when you're studying the contact and symplectic geometry of small Seifert fibered spaces. So I'd like to just kind of summarize what I've said on these last slides, just kind of a little repetition since I kind of ran through that a little fast. So we have a complete understanding of when a contact structure can bound a rational homology ball if E naught's less than or equal to -3, when E naught is bigger than or equal to 0, or when E naught equals -2 and you have an L space, there's at most 4 contact structures that have rational homology ball fillings. And here's a couple of conjectures. I think the conjecture is there's at most 1 and usually not even 1, but that's all there should be. And when E naught equals -2 and you're not an L space, remember I said nothing about the case when you're not an L space, but the guess is that you should never bound a symplectic rational homology ball. And that guess is just based on the fact that we spent months and months trying to construct even one example and kept failing. Sometimes you could even prove you couldn't do it, but mostly we just couldn't answer the question at all. But again, based on a bunch of attempted constructions, I think they just never will. So then we'd have a complete answer in dimension for E naught equals -2, what happens? So when E naught equals -1, again, we can construct lots of examples, but we have no general theorems. We have no general understanding of what might happen, except it's going to be way different than what happens for other E naughts. And a couple questions. We'll say they're conjectures. We haven't thought that hard about them. But you can ask, suppose you've got a contact structure on one of these small Seifert fibered spaces. How many different rational homology ball fillings can you have? I think the guess should be maybe 1. So I'm not talking about how many contact structures have rational homology ball fillings. I'm saying once you fixed a contact structure that does, how many different fillings could you possibly have? And my guess is 1. So I think another very interesting question that I think is only relevant in E naught equals -1 case, although I guess it might also be relevant for -2. Can you have a rational homology ball filling, one that's Stein and another that's symplectic but not Stein? So we have no idea about this. So it turns out that if E naught is not equal to -1 or -2, every filling is automatically Stein or a blow up of the Stein manifold. So, but when E naught equals -1 or -2, and when it's -2, if you're not an L space, then you can have some symplectic non-Stein fillings. But we don't know if you can do that with rational homology balls. Okay, so that's basically an overview of what we can say about rational homology ball fillings of small Seifert fibered spaces. But let me talk about a few other special types of rational homology spheres. And I mentioned earlier the spherical 3 manifolds. So again, a spherical 3 manifold is just a quotient of S3 by some isometries of S3, and they break into 5 families called cyclic, dihedral, tetrahedral, octahedral, and icosahedral. The cyclic are very familiar. They're lens spaces. The other ones are maybe not so familiar. I'll give you some explicit descriptions of some of them a little bit later. Well, in a minute here. The nice thing is Cho and Park actually completely tell us when one of these things smoothly bounds a rational homology ball. And basically, so if you have one of these spherical manifolds, it bounds a rational homology ball if and only if it or it with its reverse orientation is a lens space where P over Q is in script R, where script R is a set that that's explicitly described actually from work of Liska actually, or you're a dihedral, you're one of these dihedral spherical manifolds, and they're basically given by that surgery or that plumbing diagram at the top. So you've got that. Well, you can right? You do the continued fraction expansion of P over Q, and you basically have that plumbing diagram. And then there's these three exceptional ones. So T3 and T27, so those are tetrahedral. And then you have this one icosahedral I49, and there are the plumbing diagrams for those. Okay, great. Oh, sorry. Sorry. That parenthetical comment should be above item 3 and below item 2. See, there's a P prime up at the top there. Oh. Computer glitch. There should be a Q there. Anyway, it's an element of Q. Anyway. Okay, great. Excuse me. So what can we say about these? Well, a contact structure, any contact structure on a spherical manifold can bound a rational homology ball if and only if it's a Lens space with a canonical contact structure, and it comes. This is the exact kind of Stein filling of that Lens space. So that's it. So only the ones that Liska found. Everything else doesn't have them. But that's if you're using the correct orientation, the orientation coming from the actual orientation on S3 by the quotient. If you reverse the orientation, it turns out that we know of one example where it actually does bound a rational homology ball. So it's minus T27. But we know that minus oh, sorry. That was supposed to be, too many typos. That was supposed to be minus T3. So minus T3 is that, and it does bound. But minus T27 minus I49 do not. We checked an infinite family of the minus DPQs, and they don't either. We guess that none of them do. So there should be only this one exception, but we couldn't actually prove it for all of them. Okay, great. So now I want to move on just very briefly to mention this question of Gomph. So you have, to remind you of Rees-Gorn sphere, you just look at this equation where the PQ and R are relatively prime, and C3 intersect with the phi ball, and you get a rational homology, actually an integral homology 3-sphere. And Gomph asked the Rees-Gorn spheres ever bound Stein domains in C2 with either orientation, which would imply that they bound homology balls. So if you can prove they don't bound homology balls, you've actually then proven Gomph's conjecture. I should mention there's this conjecture of polar that basically says if you have more than 3 singular fibers, so here I just used 3 things here, but you could actually look at more terms in a higher dimensional complex space, intersect with the appropriate thing, and you'll actually get a Rees-Gorn sphere with more singular fibers. Polar conjectures that none of those should bound even smoothly bound homology balls. So if you're just looking at the 3 singular fiber case, conjecturally, this is all you need to consider. And what we can prove is for this one particular family, PQN plus 1, they don't symplectically bound rational homology balls. Okay, so I think this was just a very brief run through of kind of the things that we can prove. And for the rest of the talk, I'm going to give you a sketch of the ideas that go into proving these things. But I think it's a good time to pause. Are there any questions about the statement of the results? And while I'm pausing, I will have a little drink. Okay.
The ideas, but are they kind of the same in these different examples, or do they differ a lot?
Well, there's basically 3 things, and the first one is essential. You actually have to understand the contact structures on them. And this has been done by a series of work of a bunch of people, Wu, Gagini, Gagini on his own, Tosin, and oh, I misspelled that too. Anyway.
And understand means?
Understands means classify. So we understand what all the possible type contact structures are. And so the main text, so that's basically past work that we're just taking. So the main work that goes into this thing is there's a splitting result due to Christian and Minke that tells you how to take a symplectic filling of one manifold and then kind of break it into 2 and get fillings of other manifolds that hopefully you can understand better. And I'll describe that very explicitly a little bit later. And then Gomph came up with this invariant of homotopy classes of plane field called the theta invariant. And sometimes we need to use computations of that to distinguish things. Most of the results follow by the splitting result, but we do for some of the examples have to use Gomph's theta invariant. So I'll kind of indicate how all of those things work, as we move along. But those are the main ingredients. Any other questions before we actually get into the details? Okay. So we're going to start with the Christian-Minke result. And for this, we actually need to understand contact structures on T2 cross interval. So I have to do a little bit of background here. So maybe forget the picture up here. Just recall, if you take T2, if you look at the first homology, so a curve on T2 gives you a homology class, a first homology class. And that first homology is, of course, z plus z. So it's described by two integers. And those two integers, those two relatively prime integers, if it's an embedded curve, you can realize by a fraction in rational numbers or infinity. So all curves can be parameterized. All curves, once you fix a basis for H1, can be parameterized by an element of the kind of the extended rational numbers. And then what you can do is you can look at the Ferri graph, which is basically the unit disk in R2, and you decorate the boundary with rational numbers kind of in order, and you put an edge between any two numbers if those two numbers happen to form, when you interpret them in terms of H1, form an integral basis for the first homology. Okay, so this is a really, really convenient way of keeping track of curves on the torus. So suppose you have two things, like, I don't know, two S0 and S1 that share an edge. So for instance, -1 and -2. Then it turns out there are exactly two tight contact structures on T2 cross interval whose boundary is convex with dividing curves of slope S1 and S0 and S1. So what does convex mean? I don't want to define it. If you really want to, I'm happy to tell you about it. Actually, if you have a question, I'm happy to give you the definition, but it's not going to help us. It's a condition. It's a generic boundary condition for contact manifolds. And once you fix these generic boundary conditions, then there's exactly two contact structures. We call them basic slices. And I was remiss here. I should have mentioned Honda and Giroux basically proved everything I'm saying right here. And it turns out on the solid torus, there's a unique contact structure where the dividing curves have slope S1 and the meridian of the torus has slope S0. And lastly, any tight contact structure, let's forget solid torus for now, any tight contact structure on T2 cross interval comes from just stacking together a bunch of these basic slices. Okay. So let me just give you an example. If you've never seen this before, it's just kind of good to see how this goes. Again, I think I'll focus on the torus case, so the second case. So notice if you look at the numbers -3 and -2/3, if you look at this kind of path between them, there's kind of three jumps. And on each one of those jumps, remember, there's exactly two contact structures. So when you concatenate them and put them all together, that means you've got 2 times 2 times 2. You've got at most 8 contact structures. And it turns out that those first two jumps from -3 to -2 and -2 to -1, turns out if you have plus minus and minus plus, it's the same. So in the end, you actually only have 6. But the point is you can at least get an upper, you can list all of them, get a complete upper bound just by counting the number of jumps you have, just 2 to that number of jumps. That's all it is. Great. Well, the whole reason I was telling you about this is I have to define something called a mixed torus. So a mixed torus, T, in a manifold, is a torus that has a neighborhood, T2 cross -1, 1, such that when you split along T2 cross 0, I have 2 T2 cross intervals. And each one of them is a basic slice, and the sign is opposite. If that happens, we say that the torus is a mixed torus because it's got a mixed sign bypasses on each side. We'll come back to the mixed tori in just a second. I want to talk about a splitting of a 3-manifold. If I have a 3-manifold with a torus in it, when I cut along the torus, I get 2 pieces. Well, I guess they could be connected, but let's not worry about that case. An S splitting of M along T is the result of cutting along the torus and gluing in solid tori along each of those 2 copies with slope S. Oh, did I say? Yeah, an S splitting. So to each of those blue tori there, I'm just going to glue in a solid torus where the meridian of the solid torus goes to a curve of slope S on each of those tori. So just a very brief example, if you take the Hagar torus inside of S3 and you do the 3/2 splitting here, then you're going to have basically a solid torus with slope minus infinity up to, when I glue in, -3/2, -3/2, and then 0 down to 3/2. So this is going to correspond to the lens space L32, and this, if you work it out, is the lens space L21. So that's an example of a splitting of S3 along a torus. So we're almost ready to state the main theorem, but I do need one more piece of data. Suppose I have one of these mixed tori, right? If I have a mixed torus, it has a slope, and I have slopes for the boundaries of the two basic slices, the butt to T. I'll call those S0 and S minus 1 and 1. And if you look at the region here, I guess we can see here. So if you look at the region, so here's one of the basic slices, here's the other basic slices. So you look at the region outside of the basic slices, so it's the green region, and you look at all of the vertices that have an edge back to S naught. And so in this case, where you have the minus 3/2, 0 and minus 1, then you have these edges to minus 2/3, minus 2, and infinity. So in this case, the E sub T is those three rational numbers. So finally, here is the result of Christian and Minka that we're going to be using to prove the results. Suppose you have a symplectic filling X of a contact manifold M, and suppose I have a mixed torus T inside of M, then we can actually split the filling we can find some filling X prime of the E splitting of M, where E is an element of this E sub T I defined on the previous page. And you recover the original X from the new X by attaching a round one handle. What's a round one handle? It's simply a three-dimensional one handle cross S1, which is not too hard to break apart into a one handle and a two handle. And we'll talk a little bit more about that as we move on. But so this is the result of Christian and Minka, and it's really nice because you start with M, which might be a very complicated manifold. After the T splitting, then you have some M prime that's bounding X prime. That M prime is usually going to be a much simpler, or at least a somewhat simpler manifold. And then hopefully you can kind of bootstrap back to understand the fillings of M from the fillings of its E splittings. Okay.
How is X prime constructed?
That's a good question. So what they do is they look at kind of holomorphic annuli with boundary on the region with the mixed torus, and they then construct basically what is it, an S1 cross D2 to kind of split the manifold along, and they kind of prove that then the resulting boundary of that is going to be when you split along that, it's going to be a symplectic filling then of the manifold you get from the E splitting of M. So holomorphic curves go into the proof of this. Yeah. I mean, basically, it's kind of like, Eliashberg has this result that you have, say, a Stein filling of a manifold that's reducible. So you've got this two sphere that splits it into two pieces. He told you that you can actually split the symplectic manifold into two pieces, filling each of the pieces. So that means any filling of a connected sum is just a filling of the pieces and you attach a one handle. And this is kind of a generalization of this to the T2 case. And again, the tools and techniques are the same, although this involves quite a lot more analysis because the annuli are way more complicated than disks. But yeah. Other question? Yeah.
In this strong healing category, right?
Yeah, I was going to try to avoid that. So if X is an exact filling, then X prime is going to be an exact filling as well. If it's not an exact filling, when you do the splitting, suppose X is a strong filling but not exact, then when you do the splitting, you get a weak filling. But if your boundaries are rational homology spheres, they become strong filling. I mean, so there's some issues there, but it's not going to be an issue for us because we're talking about rational homology spheres. But there is a little bit of a subtlety when you're talking about the exact fillings, the specific fillings that you're working with. Yeah. Great. Other questions? Okay. So let me give you an example of applying their theorem. And this example actually was in their paper as well. So I'm just giving you a little proof of an application of their result that, again, it appeared in their paper. So basically, suppose you got a Legendre knot L in some contact manifold in C. You create a new contact manifold M prime C prime by doing Legendrian surgery on L. So it's a specific surgery operation to get a new contact manifold. Then any symplectic filling of M prime C prime comes from a filling of MC by attaching a Stein two handle along L. So basically, we completely understand all the fillings of M prime in terms of the fillings of M. Okay. Oh, I didn't say that. I should have said the L has to be stabilized both positively and negatively. That's going to allow us to get the mixed torus. So let me just very quickly sketch this proof for you to see how this corollary follows from their theorem. So this picture, this is of course D2 cross interval. I'm thinking of course spooling at the end. So this is a solid torus, and this is a neighborhood of L. So the biggest thing is a neighborhood of L. I picked coordinates, so the slope of the dividing curves is 0. And oh, sorry, this is the neighborhood of L. Because it was stabilized twice, this is the neighborhood of the Legendrian that I had to stabilize twice to get L. When I stabilize once, I get a neighborhood of a different Legendrian. I stabilize again, I get the neighborhood of L. So outside of L, and the outside of L exists after I do the Legendrian surgery. Outside of L, I've got a basic slice here that's say positive because it was a positive stabilization, and negative here because it was a negative stabilization. And so this is a mixed torus with slope -1. And again, those could be any integers, any 3 kind of consecutive integers. Okay? I just wanted to pick something that I could draw. Okay, great. Well, let's try to figure out what is this E sub t. In this case, remember the torus, the mixed torus has slope -1. The 2 basic slices have slope -2 to -1 and -1 to 0. So I look at the stuff outside of 0 to -2, and I look at all the vertices that have an edge back to -1. There's one. There's a unique one. It's infinity. So when I do a splitting, the only splitting I can do is the infinity splitting. That's it. That's all I'm allowed to do. And what's the infinity splitting of M? Well, when I split along the torus, I remove the neighborhood of the knot, right? And I glue back in another solid torus that has infinity slope. What is that doing? That's undoing the surgery. It just takes you back to M. Oh, I actually was going to say that on the next thing. So this thing, when I glue back in the torus with slope infinity, that's undoing the surgery, so it just gives me M back again. And the other one is the neighborhood of the knot, which is solid torus with another solid torus glued to it. If you think about it, it turns out that's just going to be S3. And S3 has a unique tight structure, so it has to be that contact structure. So the result of Christian Minke tell me that any filling, oh, that was supposed to be an X prime of M prime C prime, sorry, comes from a filling, oh, sorry. Yeah, sorry. Yeah, sorry, I think I've got a typo here, right? So it's on the board here. So you had in C, right? In C, you got M prime C prime, and if I had a filling of M prime, then this thing is going to split into a filling of M and a filling of S3. This has to be B4 as long as it's not a blow. We're making sure everything's irreducible, so it's not going to be a blow up. So it's just B4. So I have a filling of M, and then X prime. Then X prime has to be the filling X of M union B4 union around one handle. This is of course just a normal one handle and a two handle. And what happens, the one handle, when I attach it, it just connects these two together, and the one handle cancels the B4. So that just gets me back to X again. So I'm attaching a two handle to X, and if you look at their proof, you know where you're attaching that two handle. It's back to that L again. So basically any filling X prime of M prime comes from X by attaching a two handle. And that's what I was supposed to say here, but I think some of the primes and stuff got messed up, but anyway. Great. Good. Any questions about that? Great. So let's finally prove one of these results. So we want to talk about symplectic fillings of small Seifert fiber space with E naught. With E naught less or equal to -3. So, wow, moving that messed everything up. Oh, there we go. Great. So suppose you have a contact structure on Y. It's given by the surgery diagram I mentioned earlier. So Legendre surgery on the surgery diagram. So case one is suppose one of the unknots in the surgery diagram was stabilized positively and negatively. Then it turns out, using the result I just told you of Christian and Minke, then any filling of YC comes by attaching a Stein 2 handle to the result of just removing that thing, because the YC came from this thing by doing Legendre surgery on that. So we have a filling of this with a 2 handle attached. But what is this? Well, the piece over here is just a linear plumbing, so it's a lens space. And this other piece is a small Seifert fibered space again with the same E0 that I had before. Okay, but it turns out that when I have the same E0, neither the lens space, well, sorry. So any filling, actually, as I mentioned from the Eliashberg result, any filling of this just comes from a filling in each of the pieces by attaching a 1 handle. And it turns out, since both of these are rational homology spheres, well, sorry, let me say that. So the only way I could get a rational homology sphere filling of Y is if there was a rational homology S1 filling of this thing, right? When you attach a 2 handle, it would then kill the B1 and not give you any B2. So that's the only way you can get a rational homology ball filling of Y. But it turns out that because each one of these things, well, because this thing is a rational homology sphere, it can't bound a rational homology S1. It's just a little bit of algebraic topology. So basically, this can't happen. So it's a contradiction. Well, so what if each of the knots is consistent? So everything is stabilized consistently, but 2 adjacent knots are stabilized differently. So here's the picture. So I'm just drawing this stuff because I didn't want to keep drawing some complicated picture, but these are all some Legendre realizations. But here I have these 2 Legendre knots. Each is stabilized only in one direction, but they're stabilized differently. If you analyze this picture, you can actually find a mixed torus in there as well. And then you're going to wind up splitting any filling of Y into a filling of, say, X1 and a lens space, where the lens space is determined by, right? So we have this thing. So this piece here, when I split on the torus, is going to give me some lens space, and then the other piece is going to be another small Seifert fibered space, again, with E0 less than or equal to -3. So for the exact same reasons, one of the X1 or X2 would have to be filled by a rational homology S1. Neither is, because they're both rational homology spheres, so that can't happen either. So the only way that we're going to not run into trouble is if everything is stable the same way. It turns out that's exactly the Milnov-fillable thing, and those were already handled by Bupal and Stipschitz, so we're done. By the way, maybe I should mention one thing here, one small subtlety, is I didn't kind of draw the stabilizations in the central curve, but because E0 is less than or equal to -1, these things are stabilized. And that means you could have a mismatch here as well, in which case your torus is going to split it into 2 lens spaces. So you can rule out that case as well. But so there is a case that I didn't draw pictures for, but it works exactly the same as the ones I did draw pictures for. Great. Great. So that finishes actually the proof for everything with E0 less than or equal to -3. And by the way, remember, Bupal and Stipschitz said there are no fillings of the Milnor fillable things when E0 is less than or equal to -5, and so that gave us the first theorem I stated. Great. Well, what about fillings when E0 equals -2? Well, when E0 equals -2, if you happen to be in the script QHB, remember this is the family that Bupal, Stipschitz, and the rest gave us, then we know that you have this canonical contact structure that does bound a rational homology ball. So in our paper, we proved this nice inequality that it turns out that in these cases, and a few others, we can prove that if you have a contact structure that is not the canonical contact structure, then this theta invariant of Gompf is actually bigger than the theta invariant of the fillable one. So let me just remind you, the definition of the theta invariant is you take a symplectic filling, well, a complex manifold X whose boundary is your manifold, and you take a complex structure such that your contact structure is just the J complex tangencies to the boundary. And then you can kind of compute this quantity, the C1 squared for the complex structure, the signature, this thing involving signatures and Euler characteristics. This gives you a number. And it's very clear that when you bound a rational homology ball, C1 squared has to be 0, signature 0, Euler characteristic is 1, so your theta invariant is just -2. So we know for the canonical structure, the theta invariant's -2. Every other one has theta invariant bigger than -2, but if it's not -2, it can't have a symplectic rational homology ball filling. So that's the only contact structure that can have a rational homology ball filling. So this is one where we couldn't use splitting tori, so we have to use the theta invariant. So no other thing rational. Okay. So what happens if you're not in this script QHB? And y being an L space, again, remember we need that. Then again, any contact structure on there comes from surgery on the link that I mentioned before. And we can use the same arguments as above, but notice the central curve has no stabilizations on it. And because of that, I can't relate stabilizations here to stabilizations there. Because before, I knew all these things had to be stabilized the same way, but then they'd have to be stabilized the same way as the central curve. So actually, everything has to be the same or you get a mixed torus. But because you have this -2 in here, you just have this unstabilized thing, and these legs are now kind of independent. So you can just say things have to be consistent or almost consistent. You can't say that there's this unique contact structure. And this is how you get the stated result for E naught equals -2. So finally, for the other results that I want to mention, let me just kind of tell you how to build some interesting rational homology spheres, well, rational homology balls with homology sphere boundaries. So the orange here is a picture of S1 cross S2. So ignore the green. I claim if you just do a little bit of kind of Kirby calculus playing around, or Ralston calculus or somebody's calculus, then you can easily see the orange is S1 cross S2. But it turns out that when you look at the orange S1 cross S2 that way, you naturally see a Seifert fibered structure on S1 cross S2, and then that green fiber is a fiber in some Seifert fibered structure on S1 cross S2. And if you want to draw that in a different way, that green fiber is this. If you chose the R correctly, it would look something like this. Great. So notice when you see that, well, it turns out you can Legendre realize F with Thurston-Benneken equals 0 in the top figure there. And so attaching a sign 2 handle to S1 cross D3 along that fiber will give you basically a symplectic filling of that manifold. And by doing a Rolfson twist on the A over B thing, you actually get a -1 there. And these are all negative as they're supposed to be. So this thing is a Seifert fiber space with E naught equals -1. And notice, because I can do stabilizations, a lot of different sorts of stabilizations on F, this can give me Seifert fiber space with E naught equal -1 that have arbitrarily many different contact structures that have rational homology ball filling. So that's where that construction came from. Yeah, so we can get lots of rational homology ball fillings when E naught equals -1. So what if I want something besides E naught equals -1? So suppose we do P over Q surgery on F. So remember, if I do P over Q surgery where P over Q is not an integer, I can't do this by attaching a handle, right? So I can't necessarily get a rational, well, I won't get a rational homology ball. But one thing we can easily see is that if P over Q is basically in that region from 1 over n+1 to 1 over n, then the rational homology sphere that we get has E naught equal to -1 n. So we can at least build lots and lots of homology spheres this way. But how does it relate to homology ball? Because again, we can't do this rational surgery. Well, that's what I'm saying there. Well, luckily, back in the 80s, Gordon had this really, really nice observation that if you take an RS cable of a knot and do RS -1 surgery on it, it's the same as RS -1 over R squared surgery on K itself. So I can do rational surgeries by doing an integer surgery on a cable of the knot, at least some rational surgeries. Yeah, so attaching a 2 handle to S1 cross D3 along this cable will give me Seifert fibered spaces with any E naught that I like, because I can actually arrange that this number, you know, is going to be in any possible interval in there. So I can get any possible E naught I want. So this gives me smooth rational homology balls that bound Seifert fibered spaces with any E naught, no matter how negative, how positive, whatever you want. But I can't do this symplectically. I can do this symplectically only if the RS is less than 0, it turns out. And when RS is less than 0, you only get things with E naught bigger than or equal to -1. So you can't use this construction to get anything negative, which is good because we know they don't exist, at least not for E naught less than or equal to -5. But you can get things for bigger than or equal to -1 this way. So this explains almost everything that I stated for bigger than or equal to -1. Okay, good. So now is maybe time to just mention a few things you might want to do past this. So first of all, I mentioned at the beginning, you have this rational blowdown construction of fifth shell and stern that due to Margaret's work, we actually know can be done symplectically. Well, now we know we have these symplectic rational homology balls with a contact structure that is also the boundary of some plumbed manifold. So if you combine these spheres in a symplectic manifold symplectically, then you can do this construction symplectically. Can you actually get new things from this? And there's been a little bit of study of things like this, but I don't think it's been studied in quite the generality we're kind of mentioning here. So can we establish the Goff conjecture? So basically go further than what I mentioned that we can prove so far. Or maybe Kolar's conjecture was about three-scorn spheres with more than 3 singular fibers bounding smooth things. Could we try to prove it in a symplectic way, prove that it's true symplectically? So we're thinking a little bit about trying to do things like that. Well, if you actually classify fillings of quite small Seifert fibered spaces, there's been some work on that by Christian and Lee, but I think probably that can be pushed quite a bit further. And also, now that we know something, a little bit about some of the fillings of some small Seifert fibered spaces, can we say something about symplectic cobordism relations between various contact structures on small Seifert fibered spaces? So I think that's a good place to stop.
Time for questions and.
So for the Etnyre and negative 2 case, if you have like almost consistent, everything you cannot split the thing.
That's right. You can't split it, so you have to try to understand those differently. So that's why we say there's at most 4, but and that's also, remember, when the manifold's also an L space. When it's not an L space, we actually don't know what the contact structures are. We know some, but we don't in general know what all the possible contact structures are. And so we don't actually have so we don't have an idea how to prove that they couldn't have a rational homology ball. We don't know if they are. So.
So John, what do you mean by at most 4? So, but you have.
So right, if you take let's say E naught equals -2 with say that is an L space, then suppose you pick the data so that you have 10,000 different contact structures. There are certainly such examples, right? We can prove that all but possibly 4 of them cannot bound a rational homology ball, but there are 4 up to orientation on the plane field that might. I think the guess is most of them don't, but some of them might. And because of the range that they're falling in, they're not going to be links of normal surface singularity. So you can't use the techniques of Upal and Stipschitz to even get started on those. So at the moment, we just don't really know how to get started on those.
Yeah. First talk in the afternoon starts at 1:30. Should have been Separate developments. Oh, I mean,